Hello and welcome to this video on evaluating trends. Okay, so this evaluation of trends, even if you don't use this particular skill in your individual investigation, you may be asked to comment on it in a database question on the paper too, for example. Okay, so when you're evaluating data, one of the things that you can evaluate is the strength of a relationship or how well a line is fitted. So I'm going to go through those two examples now. So here, first we're going to have a look at the strength of a line. Okay, so an R-squared value is also called the coefficient of determination. The R-squared value is a statistical measure of how close the data are to the fitted regression line. The closer the R-squared value is to 1, the better fitted the line is. So the R-squared value is something that you can tick on Excel to appear on your graph. So when you fit a line, when you do a linear regression of some sort, it could be linear, polynomial, logarithmic, whichever one best fits your data, you can generate something called this R-squared value. Okay, so it's a little box that you tick on Excel and it will pop up on your graph as well as the equation of the line. So it says here the closer the value is to 1, the better the better fitted the line is. So in this particular experiment, we have the number of hours of that students study and their biology grade. This is totally made up, by the way. So you can see here that the R-squared value is 0.9753. So it's a very well fitted line. All the points lie close to that line. Okay, so this is a very well fitted line. In the second graph here, you can see that the R-squared value is 0.4761. The data points are much further removed from that line. And in this third graph here, they're all over the place, and our R-squared value is 0.0076. So that's not a very well fitted line at all. Okay. The next thing we're going to have a look at is different types of correlation. So we can see that there's a correlation here, there's a correlation here, there's no correlation here. But if we want to actually put a number on how strong that correlation is, how closely associated those X and Y variables are, we can use something called a Pearson correlation coefficient. Okay, to see what kind of correlation you have and how strong that correlation is, you can do a statistical test called the Pearson correlation coefficient. Now this is super quick and super easy to do on Excel. In fact, I'll post a link to a YouTube video on how to do that. It's super easy. So we can see here, obviously there's a positive correlation here, not really any correlation, and here's a negative one. Okay, we can see that. We can, but if we want to actually put a number on that and see how positive or how negative that is, we can do this statistical test here called Pearson correlation coefficient. Okay, so the coefficient, an R value, not to be confused with the previous one, which is the R-squared value, goes from +1 to -1. A value of +1 is a perfect positive correlation, and a value of -1 is a perfect negative correlation. The closer the number is to 1, the stronger the correlation, and a value of 0 is no correlation. So the further it is from +1 or -1, the less strong that relationship is. Okay, so here we have a very strong positive relationship, medium strength positive relationship here, very weak, slightly positive, but very weak, practically no correlation. And here is a relatively strong negative correlation. Right, final thing, and I mentioned this in the video that we talked about the liver and the catalase and the potato thing, this idea of overlapping error bars. So this is not to do with, in this case talking about trends, but looking at overlap of error bars. You can have overlap of error bars actually, where's the potato one? Here as well. In linear graphs as well, you can have overlap, and it means the same thing. Okay, so it's not limited to bar graphs, but it's easier to show with bar graphs. So when you have no overlap, that's likely that there is a statistically significant difference, but you must actually do a statistical test to draw a conclusion. Here there's less overlap, so it's probably not statistically significant. And here there is a lower overlap, so it is unlikely to be statistically significant. Again, to confirm this, to verify this, you would need to do an actual statistical analysis.